We have seen so far two different approaches to tackling algorithmic problems. We have seen greedy algorithms. This was Dijkstra's algorithm, what we saw in the graphs lecture, where we just took sort of locally the best we could do at our frontier of vertices in our solved set. Just took the shortest edge off of that we could at every step, and these local optimal decisions together constructed a global optimal solution. It's sort of a greedy algorithm approach. Sometimes it works, sometimes it doesn't. You just have to be able to prove whether it works or not. We also saw divide and conquer, which is like merge sort. We split a problem into multiple pieces, we solve each piece recursively, and then we integrate the results back into our overall solution. That's divide and conquer. A third approach that we're going to be looking at today is dynamic programming. This is just another tool in our toolbox, or if we see a problem that matches the pattern that we have been trained to recognize, that, oh yeah, this could be a good application about dynamic programming, then we use dynamic programming. So what is dynamic programming? Let's get into it. When the problem has a recursive structure with overlapping subproblems, kind of like when we saw the Fibonacci sequence in a previous lecture, and the two different terms of the Fibonacci sequence at any given step contained a huge amount of overlapping work in the subproblems. So that's sort of the vibe of what we're looking for there. We want those overlapping subproblems. Then we approach it by writing a recurrence. A recurrence is just a recursive formula that defines a sequence of numbers. And writing code to populate a table, to basically like turn that formula that recursively defines a sequence into the actual sequence. We want to reify it or materialize it into a table that actually contains all the data that we is implicitly defined by the recurrence. We'll see some examples of that. In fact, I'm going to take you through several examples of what dynamic programming looks like when it's used to solve a real problem. By the way, the term dynamic programming is another one of those unfortunately overloaded words. We have dynamic arrays where the array resizes itself automatically. We have dynamic memory management where instead of using manual like malloc and free calls, we have instead of automatic memory management where we put things on the stack, we make malloc and free calls to do sort of dynamic memory on the heap. There's also dynamic typing where like the same variable can hold values of different types over the lifetime of the program, versus static typing where a variable only holds values of a single type. There's all sorts of dynamic. Uses the word dynamic in computer science and software engineering. This is one of them. When you see dynamic programming, and you shouldn't be sloppy about this, don't call other things dynamic programming. This specifically is dynamic programming. When you write a recurrence and you write code to populate some table, it could be like a one-dimensional table, we'll see an example of that, or a two-dimensional table, we'll see an example of that. We'll also see an example of a three-dimensional table. But this is the specific approach called dynamic programming. All right, let's see an example. Let's say our first application. We are making change. We're programming a vending machine. Yes, these little devices in our everyday lives do need programmers to write code for them. Washing machines and vending machines and electronic door locks and everything. These all have code in them. Anyway, our vending machine needs to dispense change for some cash amount X, which has been overpaid by the customer, of course. So we want to minimize the number of coins that we're dispensing. So we're just counting the coins. There's some fixed, small but non-zero cost to dispensing a single coin as change because someone has to come around and restock these things, and we need to pay for that labor. And also our bank may charge us for the service of getting coins from them and stuff like that. So the machine should dispense as few coins as possible. And an additional requirement, which is kind of wacky, but it's a pedagogical expedient, I guess, to make this a little bit more interesting. The algorithm should work with any denominations of coins. So here's the denominations. Like for the US, we have pennies, nickels, dimes, and quarters. The European Union has euro cents and euros. Japan has yen. These are like all the different coins that are in common circulation in these countries. There's also some other coins in the United States that are not used very commonly. Our approach is going to be the same for all of these dynamic programming problems. It's always going to be the same two steps. This is the heart of dynamic programming. We're going to first write a recurrence, and second, write code to populate a table to like materialize the values of the sequence that is defined by the recurrence. Okay. So here's an algorithm which won't work. We cannot use the greedy algorithm here. A greedy algorithm that you might think to solve this problem is just like the way that cashiers in practice actually do make change, like in the US. If you're making change for X cents, you take as many quarters as you can without going over. Then you take as many dimes as you can without going over. Then you take as many nickels as you can without going over. And you finish out by taking as many pennies as you can without going over. And you're done. You just repeatedly pick up the largest coin that won't cause you to overshoot your remaining amount of change that you still need to make. But it doesn't work in general, because you can construct sort of degenerate cases like with weird coin denominations like 1, 4, and 6. Say you're in a country, you want to export our vending machine IP package to a country that has coins 1, 4, and 6. And someone puts in the right number of coins, then it needs to make 8 cents of change. Well, if we follow the greedy algorithm, then we'll get the 6 out because it's the largest. And then we'll have to spit out 2 1 coins, right? 6, 1, 1. But it would have been better to dispense 2 4s. That's 2 coins total. This is 3 coins total. We would have saved the value of 1 coin if we had not done the greedy algorithm approach. So strictly speaking, to solve this problem with any given denominations of coins, we cannot use the common cashier's algorithm that every cashier in the US knows. We can't use that. We have to do something different. We have to use dynamic programming. This is sort of the textbook dynamic programming question, by the way. If you see this is like, oh yeah, okay. This is dynamic programming for sure. All right. So here's our first step. You remember, it is to define a recurrence and then build the table to like materialize the recurrence. So here's the recurrence. This is going to define a sequence. The min coins of n. So we have a whole sequence of these values, one for each n. But let min coins of n be a function which value is the minimum number of coins it takes us to dispense n cents or whatever of change. So the value of this function is the minimum number of coins we need to dispense n cents of change, given the coin denomination C1, C2, C3 up to C sub k or something. Just basically all the coin denominations, C sub whatever. Then our recurrence is going to be defined as the smallest of these branches. Min coins we're making change for n minus the value of the C1 coin. So we're making change for C1 less than the amount of change we need to make, plus 1, given that we have just used up a coin. We used the C1 coin. The same thing for C2, same thing for C3. Our base case is that we're making change for n equals 0 cents. In that case, we can get away with dispensing 0 coins. This is like the optimum that we're ever going to get, is we can dispense 0 coins in this case. And that will always win the war between all these different terms in the min call here, because 0 is going to be less than everything else here, if n equals 0. All right. And all these other cases only apply when n is greater than or equal to the coin denomination. So we can't use the C1 coin unless there is at least C1 change left to make. We can't dispense a quarter if there's only 12 cents left to dispense. So I've introduced it in this generic form, but let's make it more specific so it's maybe a little bit easier to grasp. We're going to plug in the US currency values. 1, 5, 10, and 25. This is a penny, a nickel, a dime, and a quarter. So here's our denominations. We're going to say the minimum number of coins we can dispense for n cents of change is going to be the least of all these cases. When n is 0, we're dispensing nothing, then it's going to be 0. When n is at least 1, we're dispensing the best that we can do to dispense n minus 1 cents of change. plus 1, because we're dispensing a penny. Or if n is at least 5, we can say the number of coins we can get, the smallest number of coins we can get away with dispensing of n minus 5, we need to make change for n minus 5, plus 1. Same thing with dimes and same with quarters. We're saying in each of these cases, like, what's the minimum number of coins that we have to dispense if we don't have to deal with a quarter's worth of value? So we like sort of look back at our table, like to previous entries in the table where we have 25 less cents to worry about. And then we just add 1 to indicate the fact that we've used a quarter. And this is sort of the way that we recursively define our min coins sequence. I think that makes sense. Now all we have to do is build a table starting from n equals 0 and build it up towards, whatever, n equals 100, for example, if we're always going to be making change for less than $1 or something like that. We just have to build a table for n equals 0 to n equals 100. And at each step of the table, we just fill it in with a value based on whichever is less of all these cases. In each of these cases, when we have a recursive call here, a call in air quotes, we just look back at that entry in the table. Like say n is 64, then we just look back at min coins of 63 for this case, or 59 for this case, or 54 for this case. We can just look back at the previous entry in the table, because that entry, the sequence that the recurrence defines has already been computed. This is where that overlapping subproblem thing comes in. These are all overlapping subproblems. All right. I hope that makes sense, because this is going to be the same approach they're going to be following for other applications as well. So here's the recurrence copied over again into a new slide so that you can see it still. Same as before. Here's a table that we're going to be building up. N equals 0 to n equals 17, because 17 is the number that will fit on this slide. But you can go up to 100 if you want. So we have our table. We're just sort of indicating the n's here, but you don't have to store them if you don't want to. Then we have a row for min coins of n. This is like the important bit here. We're just like, this is the terms of our recurrence. When n is 5, min coins is 1, meaning that we can get away with dispensing a single coin if we need to make 5 cents of change, and that would be a nickel. Or if we need to make 12 cents of change, we dispense 3 coins. That would be a dime and 2 pennies, right? So these are like sort of telling us the number of min coins of n for any given n. And the next coin is going to be the specific branch of the recurrence, the min here, that we actually took at that step. So as we're building up this table from left to right, n equals 0, obviously min coins is going to be 0 because that hits our base case here. N equals 1 is going to be, well, the only case that can apply is this first one. None of the other conditions here apply, so it has to be this first case. So we get min coins of 0, which is 0, plus 1 is 1. So we plug in 1, and we put 1 in the next coin because we took the penny path here, the first case. And we do the same thing for 2. We get, well, it has to be this first case, so min coins of 2 minus 1 is min coins of 1, which is 1, plus 1, we get 2. So we put in 2 into our min coins box. And again, we put the penny case, so we put a 1 in. The first time that we don't take the penny case is we get across to 3, 4, and then 5. So n equals 5. We are now able to use the first 2 cases of the recurrence, right? N is greater than or equal to 1, true. N is greater than or equal to 5, true. So you have to figure out which of these 2 is the smaller. Which one's going to win the min war here? Which of these 2 cases? Well, let's evaluate both of them. In our code, we'll have to evaluate both of them and see which one is smaller. So min coins of 4 is 4 plus 1 is 5. So the first branch evaluates to 5. Min coins of 5 minus 5 is 0. So min coins of 0 is 0 plus 1 is 1. So we have 5 versus 1. And in fact, the nickel case wins. You can either dispense 5 pennies or 1 nickel, and the 1 nickel is better. It's a small number of coins. So we pick this one, and we plug in a 5 into the next coin case because we picked the nickel case, the second case of the recurrence. And this, we just go from step to step through the table, doing the same thing every time. All right? And say we're trying to make 17 cents of change, which is very convenient because it's exactly how much fits in our slide. We're trying to make 17 cents of change. Well, we can look down at big coins and see that we're going to do no better than 4 coins to dispense. That's sort of nice to know, I guess, but that doesn't tell us like which coins we need to dispense, right? That just tells us we have 4 coins to dispense. But we have enough information here in our table because we've augmented it with this next coin row. We have enough information in our table to reconstruct the actual amount of change, the actual coins that we need to dispense, right? So our next coin is 1. The first coin that we're going to dispense is a penny. So we started at 17 cents. We've dispensed a penny now. Now we're at 16 cents. And we know the best that we can do is 3 coins left to return. And the next one that we're going to return is a 1. So we dispense a penny out at the slot. So we had 16 cents. We subtract 1. Now we're at 15 cents. Here we know that we have 2 coins left to dispense, and the next one's going to be a nickel. So we subtract 5 from 15 cents. We now have 10 cents left. We've dispensed a nickel out of the slot, out of the chute. Here we have only 1 more coin to go, and it's going to be a nickel. It's going to be a dime, sorry. So we subtract 10 from our 10 cents left. We have 0 left. We shoot the dime out the chute, and now we have 0 cents left. Now our next coin is empty. If there's nothing else to dispense, we're done. So by using this next coin row, we can jump from 17 back to 16, 16 back to 15, 15 back to 10, 10 back to 0. 0 is done. And we're able to backtrace it through the table. They done goofed. We can backtrace the actual change that we need to dispense by just sort of subtracting. And that is a common pattern in dynamic programming where you have some number that is useful for constructing this table and making a recurrence that makes sense. The main coins event, what is the least number of coins I can get away with dispensing? That's nice, I guess, but it doesn't tell you what coins exactly to dispense. So you can either augment it with an additional row that has the information you need to backtrace through and reconstruct the actual thing that you're interested in. Or sometimes, as we'll see coming up, you can just get the actual sequence out of the data itself. But you need to be sort of also thinking about not just your recurrence, but also what information you're going to need or what your strategy is going to be to figure out which of these cases was taken at each step. Because that will tell you which set of coins to dispense or whatever for your given application. It will allow you to unwind exactly which of these recursive cases were taken at each step. That's a very common pattern in dynamic programming. All right, here's another application. We're just going to keep them coming. So we're given a multi-set, which is it's another word for a bag. It's a set that can have duplicates, basically. So we have a multi-set of weighted items. S equals weight 1, weight 2, all the way up to weight n. There's n of them. And we have an upper bound b. We want to find a subset S prime of S such that the sum of the subset is maximized without exceeding b. So we can say, for example, that we have some drawer that we're trying to fill up as full as possible, or a cardboard box we're shipping out items from Amazon or something, and every item has a volume, which is its weight, it's W, and we want to put as many of these items as we can into the box without overshooting our total capacity of the box, because it's not going to fit if we have a volume that is too large to fit in the box. We're assuming that they can be packed perfectly and so on. Maybe weight makes more sense than volume in that case. So the shipping service says that for this size box we can't have more than 20 pounds of items in there. So we want to take as many of these other of the customer shopping cart as possible and put them in this box without going over 20 pounds. We can pick and choose which of these items we want to take and just here I'll put as many as I can without going over 20 pounds. And that's the little microcosm. That's a little problem that we're looking at right now. There's other problems associated with, that, like how you're going to get the rest of the customer's items and shipped and so on. But right now we're just interested in, given n items that have some weights, how do we find the subset of these items that will fill up our box as full as possible without exceeding the size of the box, which is capital B. All right, as always, our solution is going to be write a recurrence and write code to populate a table to materialize the recurrence. All right, so here's going to be our recurrence. Let L of I be, here we have two variables in our recurrence now. It's going to be a two-dimensional table. How about that? Let L of I comma B be the largest sum we can obtain using a subset of the first I items. So put all your items in a row. We're only looking at the first I items for Li comma B. And we're only trying to pack in up to an upper bound of lowercase b. This is a different number than the uppercase b, which was our ultimate bound that we're interested in. Let L of I comma b be the largest sum you can obtain using the first I items up to some upper bound lowercase b, which is going to be less than our capital B that we're ultimately interested in, or less than or equal to. All right, so here's our three cases of our recurrence. The first case is obvious. If we have 0 items that we're allowed to use, we're allowed to use the first 0 items for any upper bound B that we would want. I mean, the largest sum we're going to be able to obtain is 0. We're not going to be able to include any items at all. If we're allowed to use 0 items, that makes sense, right? If I equals 0, then our result is going to be 0, no matter what B is. All right. Our second case, L of I comma B, when, well, I is greater than or equal to 1. So we're allowed to use items. It's not 0. But the bound that we're given is actually less than w sub I. So we're not actually, we're trying to find the L of I comma B. We're not going to be able to use the ith item because the weight of I is greater than the amount of upper bound that we're allowed to have. W sub I is greater than B. So we're not going to be able to use the ith item at all. So this is just the same as writing L of I minus 1 comma B. We're not able to use the ith one. It's too big to fit in with what we have left. That's what this condition is saying. If this condition holds, if B is less than W sub I, then we can just write L of I minus 1 comma B. This is going to be the value of our recurrence in that case, which we'll look back to a previous entry in the table, of course, because we're building up a table for this thing as we go. So we're just sort of copying the value from the previous row of the table into this new row. We're copying from I minus 1 to I. Because we're not able to use the ith item anyway. It's just the same as what we had before. All right, and then the third case here, if there is room for the ith item, there is room here. If we want to use it, we could. Then we have to figure out whether we want to use it or not. Basically, there's this question of, now that we're allowed to use the ith item, now that we've expanded our table out to the ith row, now we're allowed to use the ith item if we want, or using the subset of the first I items, right? For the this is how Li comma B is defined. Is we're looking at the first I items. We can take as many of them as we want, or as few of them as we want, to maximize the weight. But we want to know if we are taking the ith item or not. And the way that we find that out is to use the max of these two cases. The right case is saying we're not going to take the ith item. It is saying it's the same as here. It's the same red case. L of I minus 1 comma B. We're not taking the ith item. It's fine. We'll just take what we had before, right? If that's better than actually using the ith item, then sure, let's use it. Let's take this as our optimal case. But the other thing that is in contention for winning this max function here, for winning, is the blue case. The blue case is saying, take the best that we could do with the first I minus 1 items. So before the ith item was introduced, what was the best we could do? Let's take that, subject to the constraint that we have to be able to fit in B minus W sub I space. So we're leaving ourselves W sub I space. So we want the best that we could do with I minus 1 items and B minus W sub I space. We want the best we can do with that plus W sub I. So we've added in the ith item. So here's our cases. Blue is we're using the ith item, and red is we're not using the ith item. That's all this is doing. And we want to know which is the max, which one gives us the largest sum, the largest subset sum. All right. And then, of course, at the end, we're interested in ultimately L of n comma capital B will tell us the largest sum that we could obtain for using all n elements, all n items, and the ultimate capital B upper bound that we were interested in originally. Here's some code. So this is for subset sum. So we initialize this table 0b equals 0. So basically we're saying, again, this is the same base case as in the recurrence. If we're allowed to use 0 items out of our list of items, then no matter what the upper bound is, the best we're going to be able to do is 0. And now we have a nested loop for I from 1 to n. This is saying we're allowed to use the first 1 item, we're allowed to use the first 2 items, we're allowed to use the first 3 items, we're allowed to use the first 4 items, and so on up to n. The inner loop is the bound is going to run from 1 to the ultimate upper bound B that we're interested in. And here is the code version of our recurrence. We have this if B is less than W sub I, this is the this middle case here. B is less than W sub I. And we have to just do the best that we can without W sub I because there's not enough space for it. That's what this case says. The other case here is that there is room for it. So we just have to take the max of these two. It's the same as from the recurrence. It's just copying it over into code. I've already explained it. Now, as I mentioned, you are interested in table sub n sub capital B. This is the value for the largest sum that we can obtain with all n items staying under the full B upper bound, or exactly at it. But that only gives us a number, right? That tells us the largest subset sum we can get. But what are the actual items in our packing? That's a separate question, right? Last time we were able to backtrace through our table of change. We were making change to sort of reconstruct the actual change, right? And in fact, I would argue that we can do the same thing here. We don't even need an auxiliary row. We can just use the data that we have in the table already that we've built up so far to basically figure out at each one of these steps which side of the max that we actually took in order to obtain our current L of I comma B, right? And if we can figure that out, then we can figure out which WIs are actually in the packing or not. That's going to be our strategy, is to figure out at each step when we're filling in a single item, a single cell in the table, which of these two sides of the max was actually taken. All right, so let's see how we do that. This is an example of a table. This is the result of evaluating subset sum of 5, 8, 9, 10, 11, 12, 13, 14. These are 8 items that we're allowed to use in our packing. And our limit is going to be 20. We want to know how close can we get to 20 using some subset of these items on the left. This is our multi-set that we're allowed to use. So how close can we get to 20? I mean, just looking at it, you can see that if we use 9 and 11, we land exactly on 20. If we use 8 and 12, we land on exactly on 20. So those are perfect fittings. We've packed it perfectly all the way up to 20. And in fact, if you look in the I equals 8 row of the table and the B equals 20 column of the table, this is at the very bottom right, we can see that this is, in fact, the answer to the question. It's yeah, we can get all the way up to 20. But we don't know yet what exactly are the numbers that are in the packing. All we know is that we can get all the way up to 20. So we have a red case on the right and a blue case on the left. And we need to basically figure out for any given cell on the table which case was taken to get there. And if we can do that, then we know which of these items was actually included in the packing. And I'll show you how that plays out. So on I equals 8, b equals 20, our value is 20, right? We know this. Well, we can look at the recurrence. I've just copied the recurrence onto this slide so you can see it again, and see that like L of I minus 1 comma 20, like I of 7 and 20 is exactly the same as L of 8 comma 20, right? So it had to have been this case that was taken. Sometimes it could be a tie, I guess. It doesn't really matter. Just like take the if it is identical from the previous row, then we can just say like, all right, so we took the red branch. That's fine. Here again, we're looking at I equals 7, b equals 20. Above it is another 20. We were just taking the exact same number before, so it was using the red branch to obtain the value for I equals 7, b equals 20. And same for 6 and 20. But for 5 and 20, I equals 5, b equals 20. We look at there's a 20 in this spot, but if we go back to the definition, it is not the case that L of 4 comma 20 is also 20. This doesn't match. The 19 and 20 don't match. So we did not pull it in from the above row. We did not take the red case. It must have been the blue case. That's the only other case that's left. So it was the blue case, and we can figure out which column and which, like, we know it was in I equals 4 row because it's always I minus 1 here in every time. So we know it was the I minus 4 row. We can figure out which column it came from by just looking at the recurrence. We're looking at B minus W sub I. So W sub I, where it's at W sub 5, the fifth item, I also have in parentheses here, this is 11. 1, 2, 3, 4, 5. It's the 11th. It's the fifth item here. So we know that this was doing L of 4 comma 20 minus 11 is 9. So it was looking at 4 and 9, which is this spot right here. It's boxed in blue. And this is when it was adding W sub I. I was 5. So we added 11. I put it in bold so we can indicate that, yes, 11 is part of our packing. And like geometrically or visually, I guess the adding 11 to our packing is indicated by jumping from a column of red boxes to a blue box in a different column. So because we've done this jump, we know that we have taken the blue case at some point, which means we've added some W sub I, and the particular W sub I that's added is the one that's right after the jump. So I equals 5, which is 11 in this case, is the fifth item. So 11 is in our packing. We do the same thing here. 9 is right above a 9, or right after a 9, so it took the red case here. But then 8 does not match the 9. So we have to do a jump. We can see in the blue case, we're looking at I sub 3 comma 9 equals L of I is 2 here, comma 9 minus W sub 3 is 9. So we have a 0 in the B column. So we have jumped across to the box 0 here, and then we have red cases all the way up. So here we have another item in our packing that's 9 for when we jumped from a column of reds across to another blue. Or sometimes it could be 2 blues in a row. Just the idea is that you're changing columns. Anyway, the important thing to figure out here is like you can sort of get the sense that it is possible to recover the original packing. You don't have to memorize this exact scheme for like, how do I actually recover the original packing? Or how would I translate this visual argument into code? Because you can do that. You can just sit down and figure it out. But if you know that, like, okay, to solve this subset sum problem, I can just build this table from where one dimension is I'm using up to the ith item, and the other dimension is I'm using up to some limit b, then I can build all the way out to I equals n and b equals capital B, and then use the information in the table to backtrace through and recover the original, like the actual packing itself. If you know that much, then you can sit down and stare at this graph, or this table, and it's like, see that, okay, yes, this must correspond to this case, this must correspond to this case. And you can translate this into code. It's not that bad. So even if you don't exactly follow like the mechanics of like how this is jumping around in here, then you can sort of see the idea of like you can tell whether it must have been the red case or the blue case at any given cell based on just looking what's above it. And that tells you what W sub i's are in your packing. All right. So here's everyone's favorite question. It's a good one. What is the running time of this thing? We love our asymptotics pop quizzes, right? Well, it's something like n time theta of n times b to build the original table, right? Where n is the number of items that we have, like in our like denominations, or whatever you're gonna call them, like the number of items that we have to pick from, and capital B is our ultimate limit. Well, it's n times b to build the table, and it's to backtrace through it. You're only doing one thing per row of the table because you're always jumping up to the previous row. So it's theta of n to backtrace through the table and reconstruct the actual packing. So this looks like a linear time algorithm, something like linear time, or like it depends on both n and b, but it's polynomial. We'll say that. Could be, yeah, it's polynomial, right? But no, it's not. It's really not. You've been bamboozled. This is not the case that it is polynomial time. In fact, subset sum problem, as we'll see in the next lecture, is an NP-complete problem, which no human, as far as we know, has ever found a polynomial time algorithm to any NP-complete problem. If you could find such an algorithm for the subset sum problem, you would be a millionaire, because there is a Money Prize for this. So in fact, we don't know of any polynomial time algorithm that can solve this, and it's sort of the holy grail of computer science research. So people have tried for a long time and they can't do it. So why is that? Why is this not a polynomial time algorithm? Why is it exponential? Well, usually when you're saying, like, when you have some like input of n items, right? You're trying to sort a list of n items. We're saying, okay, we can do this in like n squared time or n log n time or something like that. Then, like the size of your input is actually n, right? You have n items in your input. It grows with n at least, or n log n. And in this case, it's not the case, right? We're just plugging in, if we go back to the previous slide, what am I looking for here? Yeah, we're just plugging in 20 as our n, or that's our capital B. But yeah, let's look at the capital B case here. Like, we're just plugging in 20 as our capital B. Simply doubling a single bit of this 20, like flipping it from a 0 to a 1, we've only changed one bit of the input. And we've doubled the amount of work that we have to do. Like, if we change this 20 to a 40, I mean, that would not be a single bit flip in binary, but you know what I mean. Say you flip the higher order bit, you can roughly double the amount of work that you have to do in the algorithm just by changing a single bit of the input. In fact, like this input is very efficiently packed in. This problem is giving us a exponential amount of work given like a linear amount of B in this slot. If we make this capital B twice as large, we have twice as much work to do. But we've only affected the size of of capital B itself by like a factor of log 2. So there's an extra 2 to the n in our running time somewhere. That's why this is technically still an exponential time algorithm, because the size of our input is so efficiently packed in It's not like we're receiving like B different items in our input. We're just receiving a single number. All right. I think that makes sense. I hope it makes sense. Yeah, in these cases, like you're actually looking at the size, your independent variable is the size of the input. So you have to be careful about these cases where you have just a number as your input and you're doing that much work, because that like it is exponential in the size of the input. The amount of work that you have to do is exponential in the size of just this number that you're given as input. It is different if you're given n items to sort, because then the size of your input grows with n instead of growing with log n, log base 2 of n. Okay. So here's another application. We have one more to go, I think. All pairs shortest paths. Oh, this is not the last one, actually. There's another one. All pairs shortest paths. So we're given a weighted graph. This is just a directed graph that has, in this case, a directed graph that has some weight or cost associated with each edge. So you can think of like distance between points on a map, or like the capacity of flow through pipes, stuff like that. But given some weighted graph, we have some abstract graph that has weights on the edges. Find the lengths of the shortest paths between every pair of vertices. So given, you might have this huge graph with lots of edges all over the place, but given one vertex out here and another vertex down here, what is the fastest path to get from one to the other? And what is the total like length of that path through all these edges? We want to find the fastest path. And we've done that for these two elements. We actually want to do it for every single possible pair of elements all at once, and return a big table of all these results. So it's going to be like if the number of vertices in the graph is n, then it's going to be an n by n table with the shortest path length in every single slot of the table. So the like ith row and jth column of the table is going to represent the shortest path length from vertex I to vertex j. Make sense? That's our problem. That's what we're trying to solve. So our approach, as always, with dynamic programming, is going to be to write a recurrence and then write the code to populate a table to sort of materialize that recurrence into actual data in memory that we can look at, and like compute values of this recurrence. All right. So this is Floyd's algorithm. This is his answer to this question: how do we compute the all pair shortest paths? So Floyd was this computer scientist in the I think 40s or 50s. Back then, computer science was just math. But he had this algorithm for doing all pair shortest paths. And he defined it this way: let D, this is some funky kind of notation, but bear with me, D of ij with k in the superscript, so D of ijk, be the shortest possible path distance from vertex I to vertex j, using only the first k vertices as internal vertices. We're going to go through exactly what that means. The k is in a superscript because it sort of emphasizes the fact that that is the thing we're going to be iterating on. It's basically just another subscript. You could have put it down in like ijk down here in the subscript. But here we've put it in parentheses up in the superscript to sort of emphasize that the k is the independent variable here. And what we're doing is at the kth step, we are using only the first k vertices as internal vertices. So here's an example showing D of 4, 7 with 5 k's with 5. So we want the length of the shortest path from V4 to V7 using only the first 5 vertices, V1, 2, 3, 4, and 5. So we have basically just drawn the graph on a piece of paper here and put a cloud around the internal vertices that we're allowed to use because it's D of 4, 7 of 5, k is 5, so we're allowed to use up to the first 5 vertices as internal vertices. These like auxiliary vertices that we're allowed to use to make a path complete. So we have completed a path from 4 to 7, 4, 7, using these as internal vertices. And our approach here, our strategy is going to be to figure this out for k equals 1. We're only using the first one vertex. Figure this out for k equals 2, which means we're allowed to use the second vertex 2 if we want. Then figure this out for k equals 3, which allows us to use the third vertex if we want. Then k equals 4, then k equals 5, then k equals 6, then 7, and 8. We keep growing k every time, and we will eventually arrive at an answer. And the reason we do this is because we can write a cute recurrence that lets us basically evaluate the situation at every given k and say, like, do we want to include the kth vertex at all or not, as we expand k out larger and larger and larger. But this is what it looks like at the specific k equals 5 step. It gives you an idea of, like, these are the internal vertices inside the cloud. We're allowed to use these to get from 4 to 7. All right. So d of I, d sub ij, k, is the shortest possible path distance from I to j, using only the first k items, first k vertices. All right, so this is the actual recurrence that we're going to be using. The base case, there's two of them, are very simple. D of ij of 0, this is saying that to get the distance from any I to any j, using 0 other auxiliary internal vertices, so nothing else other than I and j, is just going to be the weight between I and j if I and j is an edge. If there is an edge between I and j, then we just look at the weight between them. Since we're not allowed to use any other vertices as, like, internal, like, auxiliary vertices to make the path complete, like to complete the path, it's just going to be the weight, I and j. If, on the other hand, I and j is not an edge, if there is no edge between I and j, then the distance between I and j using no other vertices is infinity. There's no way to make that path. So those are our base cases. That makes sense. Those are very intuitive. Our recursive case is saying the shortest path distance from I to j using the first k vertices is whatever is smaller between these two cases. Red and blue. The red case is saying, well, we already had a path between I and j that used k minus 1 vertices. It's not even using all k. It's only using k minus 1. We don't even care about the kth vertex because it doesn't help us. That's what this is saying. This red one. We're just going to reuse whatever answer we had before from I to j with k minus 1 vertices. We're just going to reuse that. Plug that in again. We're good. We're done. The other case of the min here is the blue side. This is saying we have a path from I to k using k minus 1 vertices. We have a path from k to j using k minus 1 vertices. Let's see if just mashing these two paths together beats our old solution. So this is what the graph looks like in a diagram, like simplified. We have some path. It might go through some other vertices, but that's okay. From I to k, and we have the path from k to j. We have a path from I to j. So we can either take the path that doesn't use k. This might go through some other vertices, but that's fine. We're not using k at all. And we're comparing that to the path that actually goes through v sub k. So these are our two options. We're basically expanding out the k at each time. We're growing k larger and larger as we grow our table. And at every time that we expand k, we're taking a look and saying, does it help us to include k or not in our paths? For every single path, I to j. So this is a double for loop inside this triple for loop that is saying, for every single k, is it better to include k or not? And that's what this recurrence is doing. Yes, it's going to be an n-cubed algorithm. It's fine. That's what the algorithm is. But it's basically saying at every k step, like, does it help us to include k in our path from I to j? So we can either just go straight, like the old algorithm, the old path that we had from I to j, not using k at all, or we can go to k first and then from k to our destination j. Those are our two options. All right. Here's some pseudocode. So, for I from 1 to the number of vertices, j from 1 to the number of vertices, we're just setting table of I, j of 0, which is, so the k layer is 0 here. We're saying if we're not allowed to use any other vertices at all, it's the same as the recurrence. If we're not allowed to use any other vertices at all besides I and j, then the shortest path from I to j is just the weight of any edge there from I to j. And if there's no edge there, then it's going to be infinity. So places where there's no edge will have infinite weight, just kind of implicitly in our pseudocode representation here. Now we have our triple for loop. For k from 1 to number of vertices, I from 1 to the number of vertices, j from number 1 to the vertices, 1 to the number of vertices, our table of I, j, k, we're building up this table of I, j, k equals whichever is smaller, these two halves, the red or the blue. And it's the same as from the recurrence. I've already explained it in English. Something that is worth pointing out here, now that we have some code in front of us. Does it really matter? Does this k subscript really matter? The third, like the k dimension. I'm not talking about this one here. I'm talking about the third subscript. Because we are just reusing, like, as we build up this table, it's a two-dimensional table I by j with a k dimension behind it. And we're just constantly filling in another like layer of these k layers as we go. But each k layer is only looking at the previous k layer. And you can sort of convince yourself as you look at this that, in fact, you don't even need, like, one solution would be to just keep track of alternating k layers, like a previous and current k layer, right? Because you're only ever looking back by one every time. But you don't even need to do that. You can, in fact, just overwrite the current k layer every time as you go and just drop this subscript. And the reason that, I mean, it's going to be a little bit hand-wavy, but you can sort of convince yourself that this works. You have to do basically a case analysis. The first case of the bin statement, this one, is just copying the old value into the new layer. So if you are just basically doing nothing, then that's the same as like copying over the value. You might as well just reuse the same k layer as before and just overwrite it, right? Because it's the same value as before. You're not changing anything. The second case is a little bit trickier. You have to use an argument that's like basically that like you're not ever going to be making a path, like as you're updating like I to k, you're not going to be using k in your path from I to k because that would be suboptimal. It's a little bit like you do have to sort of look at it and convince yourself. But in any case, so the point I'm trying to make is just trust me on this, that like you can drop the k subscript entirely. We can just be continually overwriting this k layer to our table and it will still work. The code will still work and produce the same exact results. And it will also save us memory because now instead of an n by n by n table, we have just an n by n. So it's a factor of n memory saved. And here's some JavaScript code that actually does that. This is some just normal, I guess, Floyd's algorithm code. So we're going to start off with our table. This is in our graph lecture, we had our graph representation was basically nodes, like a node class. So each node was an object that had a list of adjacent neighbors that had some weight associated with them, maybe, if it was a weighted graph. This is a different graph representation. This is called an adjacency matrix. And every entry in the matrix, say I comma j entry, represents the weight of the edge from I to j, from vertex I to vertex j. If there's an x here, that represents there's no edge, and it's just going to be positive infinity weight. So this is just an alternate graph representation. You see it sometimes. It's useful. It's very fast. Computers can deal with it very well. I mean, JavaScript is kind of trash because this isn't laid out actually linearly in memory, because they're just separate objects out somewhere on the heap that are just mashed together into an array. It's not like C#, or I mean not C#, C++ or whatever, where you can actually control allocating this all as one contiguous block of memory. But you know, whatever. You can do cool graph algorithms using the matrix representation. You can do all sorts of things. You know, traversals and like finding components and finding various properties of graphs by like multiplying matrices and doing linear algebra on them. It's really cool. But this is, for our purposes, just a different graph representation. And an advantage that it gives us is that we can just use this directly as our table. We have no third k dimension because we've gotten rid of it. We've dropped those subscripts. So we just have, like, this is our I and this is our j. You know, our, yeah. We can just reuse it. We can just use the input table as our table, because the actual original, if we go back, the original, Floyd's algorithm recurrence is d sub ij, and we've dropped the k superscript here. We dropped that. Is just the shortest possible path distance from vi to vj. And that is very close to what we have in our adjacency matrix representation. Here we have only filled in the actual edges themselves, but as we evolve through the algorithm, Floyd's algorithm is going to run, it's going to start filling in these, like, the intermediate, like, paths and things. So while there's not a direct path, the direct edge between the first vertex and the second vertex that represents this x here, there may be a path through it, through some other vertex to get there. And so we can just start off with our matrix representation, adjacency matrix representation, and run Floyd's algorithm on it directly to obtain the weights of the paths themselves, and start filling in some of these x's. Or even, like, a direct edge between one and another, like this 9, for example. When I made up the original graph, I haven't drawn on a piece of paper, but like there is a faster way to get from vertex 1 to vertex 4, or sorry, vertex 2, 0, 1, 0, 1, 2. There's a faster way to get from 1 to 2 than just taking the direct edge that goes between them. You can go around through some other vertices and get there faster. So this 9 will come down as we run the algorithm. All right, and then the algorithm is just exactly what I had in the pseudocode. It finds the min between these two cases. And as a demo, it just prints out the shortest path length from v1 to v2, which is actually this 9. Yeah. So it is in fact shorter than 9 if you run the code. You can find the code on GitHub. All right. Here's another example. It's going to be quite analogous to the last one. So this is transitive closure, another graph problem. If in some graph G there's a path from v sub I to v sub j, these are just two vertices I and j, and there's a path between I and j, then in the transitive closure of G, there's an edge from I to j. So anytime that you can navigate through a bunch of vertices to get from I to j, we're going to draw an edge straight from I to j, connecting them immediately. So here's a cute diagram from Wikipedia. This is G. It looks kind of like a linked list. It's just one vertex connected to another one. And the transitive closure, like, say this vertex can reach this vertex. There's a path between them from here to here. So we draw an edge directly from there to there. And we've done that in all the cases. There is a path from the first one to the fourth one, so we've drawn an edge from the first one to the fourth one to construct this transitive closure. And our problem now is, of course, how do we construct the transitive closure of any given graph? If we're given this graph, or some complicated big graph that has lots of edges all over the place, how do we construct a transitive closure out of it? This is a very useful thing, right? Because if we want to know, like, is there a path between the first edge and the fourth edge? In the original graph, we have to do some traversal. We have to do some, like, potentially extremely costly, like, searching around the graph to try to find a path between one and the other. But if we have the transitive closure, if someone has computed the transitive closure of that graph for us already, pre-computed it, then we have a constant time lookup. We can say, is there an edge between this vertex and this one? If there is, then there must be a path between that and the original graph. So we have this neat constant time lookup now that we have the transitive closure in our pocket. Excuse me. So this is a very useful thing to have, and we want to be able to construct a transitive closure of a given graph. So, of course, we have the same approach as always. Define a recurrence and also build up a table. This is Warshall's algorithm. Another guy named Warshall from the first half of the 20th century came up with this recurrence. T sub ij of k is true if and only if there is a path from I to j using only the first k vertices as internal vertices. And notice this is the same as Floyd's algorithm, except instead of like adding up path lengths, we're just saying there is a path or not. And that makes sense, right? Like Floyd's algorithm was interested in what is the shortest path we can find from some vertex I to vertex j. But Warshall only cares about if there's a path at all between vertex I and vertex j. So it's kind of boiling it down to an even simpler problem. Like, instead of the length of the path, we just want to know, is there a path at all? But we're going to use the same approach, the same, okay, we're using this construction about saying we're only taking the first k vertices at a time. And we'll grow our k, we'll have our k layers, and grow to the next k layer by deciding whether we want to include k, v sub k, or not. All right, yeah, and then we just reuse the same recurrence. Here's our base cases. It's asking, is there a path between I and j using the first 0 vertices? That's going to be true if there is an edge between I and j. And it's going to be false if there's no edge between I and j, because we're not allowed to use any of the other vertices as internal vertices, like in our path construction. It's a 0 here. And then in our recursive case, we have t from I to j using the first k vertices equals, well, have we already found a path from I to j using k minus 1 vertices? I mean, that would be nice if we had already found a path between I and j. We're done. So it's either this red case, we've already found a path, or we have a blue case, which is that we need the kth element. We've been introduced the kth element, so let's see if we can use it. We can say, is there a path that we know of from I to k using the first k minus 1 elements? And there must be a path from k to j using k minus 1 elements. So we're going from I to k and then from k to j, both times not using the kth element. We're just like as internal vertices. We're just going from I to k through some path and then from k to j. And that will be valid too. That'll get us from I to j. That is our t of I comma j of k, right? So either we're able to get straight from I to j without using k, or we go through k to get to j. One of these cases or another. If one of them is true, or if both of them is true, then overall it is true that we can get from I to j using the first k vertices as internal vertices. Those are two cases, red and blue. All right. Here's what the code looks like. Initializing table of I and j. Our k layer starts at 0. We can just say that at k equals 0, we're not allowed to use any other vertices as internal vertices. This is going to be true if and only if ij is an edge. That's what this line is saying. So for k equals 0, that was just part of our recurrence. And then we have our triple for loop. For k from 1 to n, from I from 1 to n, for j from 1 to n, we are going to set the table of ijk equals, this is just the same thing from the recurrence. This is just copied into code. All right, and how can we, I mean, this should make sense. This is just a simpler version of the Floyd's algorithm. And we can easily pull out now that, like, table ij at the max k is going to be either true or false at the end based on whether or not there is a path from I to j. And that will basically answer our transitive closure question. In fact, the kth layer of this table is going to be just the adjacency matrix representation of that transitive closure graph. It will be, it'll have true in places where there is a path from I to j in the original graph. And it will be false in cases where there is no path from I to j in the original graph. It's just going to be the transitive closure. All right. So let's do some optimizations. First of all, we can just drop the k subscripts like before. It's an analogous argument to why you were able to do them in the Floyd's algorithm case. So we're just rewriting the same k layer over and over again, just like before. The other thing we can do, I mean, these things come up when you're trying to write the code version of your recurrence, is that you can often do these cute little tricks to try to make it more efficient. And there is one thing that you can do here, just give you a flavor of like what this kind of thing can look like. So this is the recursive case of the recurrence. I've just copied it over and given each term a different color so that we can talk about them more easily. But this is the same thing from the previous slide, or the 2 slides back. So there's something you can notice here, which is that we can just check whether this blue term is false. If this is false, then there's no way for this conjunction here to be true. The downward pointing, the opening downward chevron is and, this one is or. So if this blue one is false, then there's no way that this conjunction can be true. Because false and anything is always false. So this is always false. And it just reduces to whether this is true or not. So in other words, T, like the purple term equals the red term in this case, if the blue term is false. So we check the blue term is false. If it is false, then we're left with just this equality on the left. None of this over here matters. It's just this equality. And if we look at what that means, it's the T of I to j of k equals T of I to j of k minus 1. In other words, we're not changing anything. We're just taking what was there before. And since we dropped the k subscripts, we don't even have to do anything. We're just overwriting the same k layer as before, and we want the same value that was there before. Just leave it there. We don't have to do anything at all. So we can, in fact, guard the inner loop over the j subscript by just checking if this blue term is false. If it's false, we don't have to do anything. We're done with that like loop around the I subscript. We'll see the example of the code in a minute. But if the blue term is true, if we didn't luck out, if the blue term is true, it still helps us a little bit. Because we can just sort of eliminate this from the recurrence. We know it's true now. So true and anything is just going to come down to whether the other thing is also true. So we can write, in the end, just purple equals red or green. Purple equals red or green. That is if the blue term is true. So we have an if statement. Let's look at the code. It's the same code as before up here, same as before, but now we have an if statement. If table ij is true, then we do the inner loop. If not, we don't have to do the inner loop at all. But if we do the inner loop, then we only have this simplified thing here, where we don't even have table ik in there like we did before. We've also dropped the subscripts in this version compared to the previous pseudocode. All right, code for all this is on GitHub, and PDF of the slides and so on, if you want to take a look. I hope this was helpful. Dynamic programming can be, it's going to be an adventure every time that you try to solve a problem with it, because you know you're going to have to be drawing tables and trying to figure out like what the recurrence is, and it's not so much like, oh, I have this flash of insight that's going to solve the problem right away. It's like, okay, I've got a slog. I've got a lot of work to do here. But it is also, when it works out, I mean, it's pretty straightforward. You just like write your triple for loops or however many for loops you need, and you end up with this nice compact looking code that's very cute. You can solve lots of problems this way. Remember, when you have overlapping subproblems and the problem has like a recursive structure, then it's a good thing to reach for. Yeah, I guess that's it.